prepared for the Federal Highway Administration by the United States Geological Survey. The material in this slide presentation was taken from a study initiated by the Federal Highway Administration to determine the causes of hydraulic problems at bridges and to identify the countermeasures that have proven most effective. In the research report, guidelines are provided to assist engineers in selecting measures to reduce bridge losses from scour and bank erosion. The report is based on case histories of 224 bridges in the United States and Canada and on interviews with engineers in 34 state highway agencies. A hydraulic problem at a crossing is defined as an effect of stream flow, tidal flow, or wave action that results in an immediate or potential disruption of traffic. This is an example of a hydraulic problem: lateral stream erosion at a bridge abutment. A countermeasure is defined as a measure either incorporated into the design of a bridge or installed separately at or near the bridge that serves to prevent or control hydraulic problems. This is an example of a countermeasure for lateral erosion. For the evaluation of countermeasures and the analysis of hydraulic problems, many factors must be considered. The relationship between these factors is represented in this scheme. A bridge crossing is represented at low flow by a set of bridge factors, a set of geomorphic factors, and a countermeasure, as shown in the top row of boxes. If a flow event occurs, either a flood or a high flow within the banks, the performance of a countermeasure is tested by its interaction with the various factors. A hydraulic problem may result from the design of the bridge, the placement of the crossing, or from man-induced factors that were not foreseen at the time the bridge was designed. If a hydraulic problem does develop, new or additional countermeasures may be installed, and the sequence of testing will be repeated at the next flow event. It is important to remember, however, that a countermeasure which performs well on one type of stream may perform poorly on another. A hydraulic problem is described according to its location, the physical process involved, and the effect on bridge use. In this example, the problem is at the bridge abutment, and the process is described as lateral erosion. The most common hazards are lateral erosion, general scour, and local scour. Other processes include channel degradation, accumulation of debris, and abrasion. The relative importance of lateral erosion, general scour, and local scour in contributing to hydraulic problems at study sites is indicated here. Some effects of lateral erosion at bridges are shown here. The upper diagram represents a bridge with vertical full-height abutments located on a stream bend. Erosion along the bank at right has been accompanied by the growth of a bar in the bridge waterway at left. The lower diagram represents a bridge with spill-through abutments, which have a fill slope on the streamward side. The erosion shown may occur at a bend or by channel widening. This bridge on Spearfish Canyon in the Black Hills of South Dakota provides an example of lateral erosion, in which the stream breached the road embankment adjacent to the abutment. In this example, lateral migration of the channel has overtaken a pier that was originally on the floodplain, exposing the footings and support piling. This problem is most common on large streams, for which the capacity for lateral migration is easily underestimated. General scour is usually a consequence of constriction of flood flow by the bridge and approach embankments. General scour may affect all or part of the bridge waterway, and it may also occur on the floodplain. Typically, general scour is only a problem in large floods. Channel degradation, which produces a similar effect at a bridge, is not primarily caused by flow constriction and is not confined to the vicinity of the bridge. It may extend for miles along a channel. The most common causes of channel degradation are stream channelization and mining of stream bed materials. At this relief bridge on the Tombigbee River in Mississippi, during a flood with a recurrence interval of 65 years, general scour occurred to a depth of about 15 feet in the channel. and was attributed mainly to eddies in the bridge waterway. Flow distribution in the waterway during later floods was much improved by the installation of spur dikes. Effects of channel degradation attributed to gravel mining are shown at this county bridge on Cache Creek in California. Local scour was identified only at those sites where scour was known to be localized at a pier, abutment, or other obstruction to flow. Its effects are superimposed on those of general scour, and it probably occurs during every flood when measurement is difficult. Local scour is attributed to diving currents or to eddy action at an obstruction to flow. Local scour occurred at these bridge piers on the St. Francis River in Missouri during a flood in 1957. Local scour may be greatly increased by accumulation of debris. This bridge on Henry's Fork in Idaho survived the major surge of flow from failure of the Teton Dam, but subsequent scour associated with accumulation of debris caused failure of a pier. In the preceding slides, hydraulic problems were illustrated according to the process involved, whether lateral erosion, general scour, or local scour. In this slide, problems at study sites are categorized according to extent. Only sites where the cause of failure could be determined or the performance of countermeasures could be evaluated are included. For this reason, bridges totally destroyed in catastrophic floods are mostly excluded. A crossing of the Grand River in South Dakota illustrates problems typical of many crossings at bends. The left abutment is endangered by bank erosion at the outside of the bend, and a point bar is developing in the bridge waterway. But the location of crossings at bends does not necessarily lead to hydraulic problems, and none have been reported at this bridge. On stable meandering streams, which are usually of uniform width, lateral migration rates tend to be very slow. Flow constriction that occurred during an extreme flood led to damage of abutment fill slopes at this bridge. Concrete pavement on the slopes, although damaged, probably prevented damage to the bridge structure. Effects of skewed piers on flow is shown at this bridge on a small stream in Pennsylvania, where a scour hole has formed at the right-hand side of the pier. The riprap at right provided protection for stream banks and abutments during a severe flood. Encroachment of abutments on a channel may cause flow constriction during a flood and consequent bank erosion by eddy action downstream from the bridge. At this bridge in Nevada, rock riprap was dumped into the area eroded during a flood in 1952. The flow direction is from left to right. Other bridge factors contributing to hydraulic problems include location of the crossing near the entrance of a tributary, as at this bridge on the Susquehanna River. Outbuilding of an alluvial fan by the tributary caused flow concentration and scour at the piers. Piers of an upstream bridge may induce turbulence and local scour at a downstream bridge, as at these dual bridges on the Snake River. Geomorphic factors include the properties of streams and drainage basins. A stream type represents a common association of stream properties. Alluvial streams may be classified for engineering purposes into major types, each having characteristics of lateral stability and behavior that need to be taken into account in the design of bridges and countermeasures. Equal-width point bar streams, which have the greatest lateral stability, are relatively narrow and deep. Wide-bend point bar streams have more rapid rates of lateral migration at bends, although straight reaches may remain stable for long periods of time. Braided point bar streams are characterized by rapid shifts in the position of the thalweg and by rapid rates of lateral migration. Braided streams without point bars have moderate rates of lateral migration at random places where one of their multiple channels impinges against a bank. The channels shift at random within the bank lines. A stream is said to be ana-branched where the flow is divided by a large island. An ana-branched stream may require more than one bridge, unless the flow is artificially diverted into a single channel. The classification just described applies to streams flowing in alluvium. In general, relatively few hydraulic problems are reported at bridges on bedrock channels. A good example of an equi-width point bar stream is the Red Lake River, which has a very slow rate of lateral migration. The Pearl River in Mississippi is a good example of a wide-bend point bar stream, which has a moderate to high rate of lateral migration at the outside of meanders. Rapid lateral migration is suggested, but not necessarily established, by the presence of many oxbow lakes. A very high degree of lateral instability is indicated by these sequential aerial photographs of the Cimarron River in Oklahoma, which is a braided point bar stream. Changes during the 30-year interval between photos were so great that the location does not appear to be the same. The rapid channel changes were due primarily to the effects of drought on plant life, and the channel has become more stable with the regrowth of vegetation. The Little Delta River in Alaska is an example of a braided stream without point bars. Such streams are fairly common in the western United States, but are rare in the east. They can be successfully confined at a crossing by suitable countermeasures, and a bridge much shorter than stream width can be used. At the bridge site shown in this aerial photograph, the Klickitat River in Washington is anabranched. Of the two bridges, one was damaged during a flood because it received an unexpected portion of the divided flow. Man may also be regarded as a geomorphic agent, and some works of man have contributed to hydraulic problems at bridges. Of the 224 bridge sites in the study, 35 were affected by stream channelization, which led to channel degradation, lateral erosion, or both. 12 sites were affected by gravel mining, and 15 were affected in one or more ways by dams and reservoirs. However, the more general influence of dams is probably to lessen hydraulic problems at downstream bridges, both by a reduction of flood peaks and lateral erosion rates. Following channelization and clearing of the forested floodplain, the Forked Deer River in Tennessee widened laterally and undercut pile bents on the floodplain. In this photograph, one of the dual bridges is being rebuilt, with piers and pile bents that have deeper foundations. Also, note that additional protection is provided by the retard upstream from the new bridge. Commercial excavation of sand from the Sand Creek in Denver, Colorado, has resulted in severe channel degradation and lateral erosion. Several bridges have been endangered, among them the Quebec Street Bridge, shown here. Check dams have been used as a countermeasure for degradation, and bank revetment for lateral erosion. Channel degradation has occurred downstream from some dams, causing the exposure of pier foundations, as at this bridge on the American River in California. The sediment load of the stream is trapped in the reservoir, and a new sediment load is acquired by erosion of the bed and banks downstream from the dam. This bridge on the Sulphur River in Arkansas was built in 1931, and no hydraulic problems were reported until after closure of an upstream reservoir in 1953. Sustained flow releases, above normal but below bank full stage, evidently increased the rate of lateral erosion. The right bridge abutment was most affected because it is at the outside of a bend. Lateral erosion at the bridge and along the channel downstream was increased by removal of natural vegetation and by a natural tendency of the banks to fail by slumping. The countermeasures in most general use, apart from those incorporated into the bridge structure, are classified as shown here. Revetment provides an erosion-resistant surface for a bank or embankment, and bed armor, which consists of the same materials, serves the same function for the channel bed. Flexible revetment has the property of conforming to minor changes due to subsidence or erosion of the underlying surface. Rigid revetment does not conform to such changes and thus may fail because of lack of support. Flow control structures serve as countermeasures by controlling the direction, velocity, or depth of flowing water. Other countermeasures are classified as shown here. Measures incorporated into the bridge structure by design, such as pier shape and depth of foundations, are essential for the prevention of hydraulic problems. However, the emphasis of the research study was on countermeasures at existing bridges. Dumped rock riprap is the countermeasure in most general use. Its effectiveness depends mainly on the adequacy of the rock size and on provision against undermining at the toe and ends. In this example of riprap installation, a rock-filled trench is provided for toe protection. At this skewed crossing, a riprapped embankment has effectively prevented bank erosion and served to direct flow through the bridge opening. A bridge on the Yuba River in California provides an example of pier protection against severe channel degradation. Since the bridge was built in 1913, the channel has degraded about 27 feet. Foundation piles were protected by a concrete grout curtain, and large riprap was placed around the pier. These countermeasures have been effective. At some bridges in Oregon, dumped riprap, keyed or plated by tamping with a heavy steel plate, has proved to be advantageous. Keyed riprap is more stable than loose riprap, and its cost is reported to be less because a smaller volume of rock per unit area is required. Rock and wire mattress consists of a small riprap enclosed between two layers of wire mesh. It is used mostly on ephemeral streams in arid or semi-arid regions, where the wire is less subject to chemical corrosion or continuous abrasion. The mattress shown here effectively protected stream banks during a severe flood in the Black Hills of South Dakota. Rock and wire mattress held in position by steel rails is called rail bank protection in Arizona. Although severely damaged during an extreme flood, this rail bank protection prevented structural damage to the bridge. On many ephemeral streams, particularly in the Great Plains and Rocky Mountain regions, channel degradation takes place by the upstream migration of steep channel scarps or head cuts, like this one in Nebraska. If a major scarp migrates through a bridge waterway, the channel may be degraded by 10 feet or more. At this bridge in Wyoming, a rock and wire mattress has been used to diminish the degradational effect of a head cut at the Orange Pointer. The mattress extends continuously across the channel bottom from the side slopes. Although concrete slope pavement is in general use at bridges in several states, it requires substantial toe and end protection from undermining. Failure, when it occurs, tends to be progressive, as at this bridge. The damaged concrete pavement was replaced with concrete-filled fabric mat, which has not been tested by a flood at this site, but has proved satisfactory at other locations. It has some construction advantages over concrete pavement and has less effect on flow conveyance than riprap. In places where rock riprap is not readily available, sacked concrete revetment is sometimes used. It has the advantage of neat appearance, but like other rigid revetment, is subject to progressive damage by undermining. Sacked concrete installed in 1956 at this bridge site in Nevada has proved to be effective. Concrete grouted riprap, shown here between the red markers, has been used effectively as bank protection on many mountain streams in California. But penetration of the grout into the rock interstices is essential for good performance. Bulkheads are particularly useful where bank failure occurs by slumping. At this bridge site, slumping affected both the abutment fill slope and the adjacent stream bank. The abutment was protected by a steel sheet pile bulkhead. Flow control measures, of which the major kinds are shown here, are classified according to their function and their position relative to the stream crossing. Other terms are applied to these same structures by many agencies. For example, spurs, which are linear structures projecting from the bank into the channel, are referred to as jetties, groins, and deflectors. One agency applies the term dike to all these structures except the jack field. The term dike was restricted in this study, however, to linear structures outside a channel for control of overbank flow. The Washita River near Davis, Oklahoma, is a wide-bend point-bar stream having a rapid rate of lateral migration. Flow control and bank protection measures are needed to maintain a stable alignment at the bridge. When a new bridge was built at this site, a spur dike, shown at the right, rip-rapped banks, and short rock spurs were used as countermeasures. Spurs may not be effective for flow control at a sharp bend near the bridge. At this difficult crossing situation, bank erosion, shown at the orange marker, has occurred downstream from 5 timber pile spurs, and the channel has continued to migrate laterally. Additional spurs or a retard may be needed just upstream from the bridge. As a consequence of channelization, lateral erosion on the Soldier River in western Iowa endangered the bridge abutment. Steel H-pile spurs were installed as a countermeasure in 1965. By 1967, the upper photograph, the spurs had induced deposition along the bank, and vegetation was becoming established. By 1976, the lower photograph, willows had become well established along the stabilized bank. These timber pile spurs on the Big Black River in Mississippi, installed in 1950, have successfully controlled the problem of lateral erosion at the outside of a bend. Patented permeable spur jetties, like these on the Brazos River in Texas, have performed well at some pipeline crossings. Permeable panels of timber and steel are loosely bolted to vertical steel pipe pile. The panels slide downward to maintain contact with the stream bed, an important requirement for a permeable spur. Sheet pile spurs have proved useful at several sites in South Dakota, where ice and drift may damage other types of spurs. This steel retard on the Tombigbee River in Mississippi has protected the bridge abutment from lateral erosion. A timber pile retard at the left on the Washita River in Oklahoma has been effective in controlling bank erosion. A disadvantage of timber pile structures is their vulnerability to damage by fire and vandalism. Overbank flow that is diverted along an approach embankment may produce eddies and scour where it enters the bridge waterway. A spur dike intercepts this flow and moves the point of scour to the tip of the dike. At this bridge on the Susquehanna River in Pennsylvania, overbank flow is constricted by the approach embankments. Passage of 2 severe floods without damage to the bridge is attributed to the spur dike. However, a spur dike may not be an effective countermeasure for unfavorable channel alignment. At this difficult crossing situation, the stream is anabranched or split into 2 channels. Lateral instability of the stream is attributed to gravel mining. During a flood, the upstream side of the spur dike was eroded and flow impinged against the approach embankment. The Snow River in Alaska is a wide braided stream, confined at the crossing by approach embankments to about 20% of its natural width. Flow is guided through the bridge opening by curved spur dikes. Check dams are usually built as a countermeasure for channel degradation. They have performed satisfactorily on many small streams, but scour of bed and banks downstream from the dam is a common problem. Here, a check dam of concrete grouted riprap is being undercut by scour. At this site, a channelized stream has been widened and deepened downstream from a check dam. This bend on the Cheyenne River in South Dakota has been successfully stabilized by a jack field. Among the requirements for good performance of jacks is an adequate load of sediment and debris in transport by the stream. Jacks used by highway agencies are usually made of steel, but these jacks installed by the Soil Conservation Service on the Tallahatchie River in Mississippi are made of concrete. Good performance of the jacks in stabilizing banks is reported. Some results of our investigation will now be summarized. Lateral stream erosion, which exposed these pile bents at a bridge in Mississippi, is the most common cause of hydraulic problems at bridges. Hydraulic problems at a bridge can be foreseen from bridge factors, such as the location of a crossing at a bend, as in this example. Problems can also be foreseen from geomorphic factors, such as lateral stream stability. The past behavior of a stream, as determined by comparison of sequential aerial photographs, is an indication of its probable future behavior. Among the flow factors to be considered is the distribution of flow in the bridge waterway during a flood. At this site, high water velocity and general scour is attributed to flow contraction at the downstream bridge. Dumped rock riprap is a proved countermeasure for protecting stream banks and bridge abutments when applied according to established guidelines. In many states, however, riprap of good quality is prohibitively expensive because it must be hauled for long distances. Concrete slope pavement is a satisfactory countermeasure for erosion of abutment fill slopes if it is protected from undermining at the toe and ends, either by a cut-off wall or by riprap, and is properly designed to resist hydrostatic pressure. Permeable spurs, such as these on the Grand River in Missouri, do not require the use of riprap and have proved effective for bank protection and control of flow alignment. It is important that the facing of the spur be in contact with the stream bed. Retards like this one on the Nishnabotna River in Iowa are suitable for control of flow alignment at sharp bends near a bridge. Spur dikes have been generally successful for control of overbank flow where it enters the bridge waterway, and no dissatisfaction was found with the curved shape in general use. Where spur dikes are used for control of channel alignment, the curved shape is not necessarily advantageous. Many bridges have resisted flood forces for a long time without the use of countermeasures. Before the advent of modern highways, channels were altered and road grades, elevations, and alignments were adjusted to suit the bridge design. Today, however, engineers are often faced with the task of providing crossing designs at a predetermined site chosen with little concern for river mechanics. Under these conditions, the potential for hydraulic problems is greatly increased, and stream sites which do develop problems can be stabilized with the prudent use of countermeasures. Countermeasures offer flexibility in seeking solutions to hydraulic problems and should be considered another highway engineering tool for getting things done right. They are needed to ensure the safety and normal design life of highways built in the river environment.